So in chapter 11, we've been looking at solutions. We are going to continue to look at a few of these terms here. On the next slide, we had looked at sodium chloride and ethanol. And so now we're going to add a few more vocabulary words to our solutions conversation. So that's going to be this page here. So the first vocabulary words we want to look at are unsaturated versus saturated solutions. And remember, most of our solutions, or every solution we've seen so far has been homogeneous. So unsaturated is what we're used to with like the table salt. So I have my solvent, got some water, and then I have my solute. If it's table salt, I've got some positive and negative ions. They're spread through evenly. So this would be like NaCl aqueous. And I would say that all of my solid dissolves. And so that's what we call an unsaturated solution, when all of the solid can dissolve. On the other hand, a saturated solution, if you've ever had a kidney stone or gallstone or gout, or know someone that's had those, I haven't, I hear they're all awful. But basically what happens is you have a chemical that will dissolve, like say my salt, but then you have too much solid for the solvent to break apart. So you literally run out of solvent to break this apart. So I start with an unsaturated solution, but then eventually I have this ionic compound sitting at the bottom here, and it can't dissolve. So some of it dissolves and some of it just stays as these chunks at the bottom. So here I would say if it's a saturated solution, some solid is undissolved. And that's because, if I can go back to this picture here, I literally run out of waters to surround that solute. And so once I run out of waters, I just have a salt crystal sitting there still. That's the solid at the bottom. So that's unsaturated versus saturated. The next terms we want to look at are miscible and immiscible. So looking at miscible, this would be like we saw on the last page where we have ethanol. And we say that ethanol mixes in all proportions with water. So they are miscible. So C2H5, OH, and water are going to mix evenly with each other. So I've got my solvent, my solute, and it's an even mix. In contrast, if it's immiscible, then I would have something like the two layers that we looked at on the first page. So gasoline, C6H14, and water. So if my solute is the gasoline and my solvent is water, they're not going to mix. And this is because if I can go back to chapter 8 and chapter 10, this is a non-polar compound and this is polar. They don't have enough in common. Here the ethanol and the water are both polar, and so they mix, but when they're too different, they're not able to mix. So I would say here that I have layers and they do not mix. All right, so that's our next two vocab words. Coming down here, one more thing we want to think about with solubility is how does gas pressure affect this? And if you've ever drank any carbonated beverage and then let it sit for a while, you know this already. So we're just going to put kind of science words on it. So let's say you have, I'm going to call it soda. My husband likes to call it pop because he's weird and he's from the Midwest. He just walked in the room, so I'm making fun of him. So if I have 2 cans of soda and this one's closed, okay, so this is a closed can of soda. And then this one is going to be an open can, and we'll get to that in a minute. So inside of both of these cans, we have carbon dioxide gas that is dissolved in water. And so again, it's a solution, right? So we have our solute and it's dissolved in our solvent. So if I can look at what's happening in the closed soda can, they don't fill it all the way up to the top. So I have some liquid and then I have some bubbles dissolved in it, right? That's why it tastes fizzy when you drink it. They also put a little bit of carbon dioxide on top of that. And so how I would describe this is I would say that I have high pressure of CO2 above the liquid. And so as a result, that gas is getting pushed down into the liquid. So when my can of soda hasn't been opened yet, there's a lot of carbon dioxide dissolved. So I would say that I have high gas solubility here. Oh, move it up. So when I have high pressure of the gas above the liquid, then I'm going to have high solubility of that gas in the liquid. Over here, once I open the can of soda, what happens to all of that fizz? It's going to gradually go away, right? So if I let this can of soda sit here for a couple of hours now, then I still have my same liquid in it, but some of that carbon dioxide, even though we can't see it, starts to immediately leak out of that open can. I've still got maybe a little in here, but little by little, that carbon dioxide that was dissolved starts to quickly evaporate, or not evaporate, but diffuse out of the can. So here I would describe this as having a low pressure of CO2 above the liquid. And so as a result, I have low gas solubility. Incidentally, the same thing happens too where you lose your fizz if you warm this up, and this is an issue with lakes and oceans. As they warm up, some of the dissolved oxygen starts to leave, and now your organisms that depend on oxygen don't have it because that gas has basically heated up and moved out of that liquid. All right, so we've got a couple terms up here. We've got this gas pressure effect on solubility. The last thing we're going to look at here is like dissolves like, and we kind of saw that already here, so that's why these two belong together. So when we say like dissolves like, we mean that if the solvent is similar to the solute, they are going to mix. So I could also say like mixes with like. Or another way that we could say it is like is soluble in like. Or like is miscible. We can mix it with like. So all of those, dissolves, mixes, soluble, miscible, they're all the same thing. And this would all be that my solvent is a lot like my solute. And we saw that up here, right? If the ethanol was polar and the water was polar, they mixed. But here where I had non-polar, it didn't mix with the polar water. So I could say that what I mean by like is that we have similar polarities, and with that comes the ability to have similar intermolecular forces, participate in those attractions. I can frame this finally in two more ways to drive it home. Polar compounds will mix with polar compounds like we see up here. Or we could also see, I haven't given you an example of this, but non-polar compounds will mix with non-polar compounds. So we're just going to look for similarities in polarity, and that will help us predict what's going to mix. So that gives us some vocabulary. Next up, we'll start to work on some problems for this.